Today in this video, we're going to be talking about random variables. If you have not already read the article on page 209, please do so because it's going to be related to what we're talking about. A random variable is a variable typically represented in a math textbook by an x. And it's just a single numerical value that has to be determined by chance. That's the part when I say random, that's what I mean. Avoid the desire to actually make a calculation with it necessarily. It has got to be something that should be determined by chance. For example, the length of the time it takes a person to finish a test. They got short ones, they got ones that take a long time, and so a specific person would have X amount of time that they took to take the test, but it's determined by the chance of how long that particular person takes to finish tests. The number of songs played by a band on a concert, that's going to be something that varies, and it might not be determined by chance by the band on the spot. They will, of course, already discussed that. But if you were to be sampling, say, 300 different band concerts, they're going to have different numbers of songs that they performed. That would be so you'd randomly then choose certain numbers of bands, which bands, that would be the part that's determined by chance. A probability distribution is then giving some description of the probability of each of those random variables. But going back to the band, let's say that there was a band that played 15 songs out of, let's say there's 300 bands and 12 of them played 15 songs. Okay, well then you'd have 12 out of 300 would be the probability determined by chance of that occurring. So that's kind of what we're talking about here. And we can describe these probability distributions with graphs or tables or even with formulas. A probability distribution will describe what will probably happen because, of course, we're determining it by chance, but what will probably happen. So we will be, of course, associating each variable with a specific probability of that variable occurring. Instead of descriptive statistics, which described what did happen. When we did descriptive statistics earlier, we were always looking into the past. This is what we saw. This is what we measured. With probability distributions, the graphs might look exactly the same. The difference is we generated them with probabilistic models instead of data that had already been accumulated. So for example here, let's say that somebody rolls dice a bunch of times, a die, just to go singular here. Of course, the outcomes would be 1 through 6, and let's say that this was how many each occurred. So the X in this case, the X is, well, did the 1 show up on the die, or the 2, or the 3, or the 4, or the 5, which one showed up? That's the X, determined by chance, by rolling it. And then this is the distribution right over here. This chart is the distribution. It's showing you how many times each thing showed up. And in this case, it's a probability distribution because, of course, we're talking about the probability of each one of them showing up with this particular experiment that was run right there. To qualify to be what we call a probability distribution, there are a couple of qualifiers, and I promise you right now, on a test, I'm going to give you some information, and I'm going to say, is this a probability distribution? This is where reviewing is important because this is section 1 of this chapter, and it'll have been a long time ago by the time you see this. And these pretty much, they're kind of almost common sense, which also makes them very easy to forget. So make sure you put a little star maybe in your notes next to this. For something to qualify as a probability distribution, it must satisfy these conditions. 1, the probability of each thing, whatever the thing is you're talking about, like we just talked about the dice rolling, the probability of it has to be between 0 and 1. Remember, 1 means it's certain, and 0 means no chance at all. Okay, since it's a probability, it's got to be between 0 and 1. The second thing, the sum of all the probabilities must add up to 1, must be 100%. So if this is actually a probability distribution, you'd have to add up all of these, which of course we can't do it on the graph because I can't necessarily read exactly what this one is. But if you have the numbers, You can add them up. If they don't add up to 1, which of course again represents 100%, then it doesn't qualify as a probability distribution. For example, this one right here, this is a study done by Scientific American, kind of an interesting, I guess, from a data point of view, on people's favorite numbers. Not necessarily favorite number from 1 to 10, just like, what's your favorite number? And the one that reigns is the number 7. 9.7% of the people said that was their favorite number. But if you look down here, okay, there's pi. So obviously these are kind of a little bit random. So people said 0, which I thought was kind of interesting. The fact that anybody knew enough to say E, but notice there's not very many of them. But what I want you to notice right here, this would not, even though we're looking at probabilities, what's the probability of someone liking 7 the most? Well, 9.7% chance. It's not a probability distribution because it doesn't add up to 100%. Obviously, there's some numbers that didn't show up in the list that Scientific American didn't include to cover the other 17.9% of these. So that would not qualify as a probability distribution. When we talk about these random variables, like in the last thing, the random variable was what's your favorite number, or what number comes up on a die, things like that. Those are the random variables. We have 2 kinds. One's going to be easier to pick out as it's going to be more common to talk about. And then the other one, you really kind of just need to know the definition to recognize it when you see it. The first kind, the more obvious one, is called a discrete variable. Discrete numbers are finite numbers of outcomes that can be listed. They can be counted. That's kind of probably how you want to think of this. They can be counted. And then you have continuous random variables. An uncountable number. I've got a scale here. On this scale, obviously you step onto the scale. Let's say it says, 163 pounds. Well, you're probably rounding it, and we all know that you should know there's 16 ounces to a pound, but you know that there's weights between the ounce markers too. In fact, whatever number you pick on a scale for weighing, I can find a smaller number that goes in between numbers like that. Same with like numbers on a ruler when you measure length. Length is a continuous random variable because whatever measurement you say, they say, 5 inches, it's 5 3/8 inches. Well, I could find a smaller unit than that. And so there's numbers between the numbers. That's what this is. Anytime there's numbers between the numbers, that's a continuous random variable. If there's not, like cars, there's 1 car or there's 2 cars. I love this picture. There's not a half a car spot. Okay, if we're counting car spots here, there's no such thing as a half a car spot. It just doesn't work. We can count them. That's a little bit different than it is with length. Continuous things are when we measure. Discrete things are when we count. So you could go out and you could take the heights of a whole bunch of students and you could set up a probability distribution. This percent of students are 5 feet 5 inches. This percent of students is 5 feet 6 inches. And even though to make a graph, you might be listing them off where it looks discrete because you did 5, 5, and 5, 6. In reality, we know that there's an infinite number of height possibilities between 5, 5, and 5, 6. I mean, just tiny, tiny, tiny measurements, which are very difficult to do. We always round our measurements. Some examples here, choosing whether it's discrete or continuous. Numbers of sales calls. If you're working for a company that makes out calls to try and sell stuff, well, you can't have a half a call. This is kind of the easy way to do it. Can you have a half of something? In which case, that's going to be discrete. You just count them. Amount of time spent on calls. Now that we measure. We measure it with obviously seconds, minutes, hours, and even between 2 seconds, we know we can break that down into smaller increments. We measure it, so that would be continuous. Cans of pop consumed. We're counting cans, that's discrete. But the amount of pop consumed, well, the more you pour, the higher the level gets. We're measuring the level or the volume, so that would be continuous. And again, if you make graphs of these, the graphs all sort of look like they're all discrete because you make a bar chart or something like that. But this is where the understanding that when you're looking at a graph that there might be more stuff involved, a little bit of common sense here has to come into play. So age, height, weight, we usually round those. Well, I'm going to go back to this. Weight, I'm going to say is continuous. Height, I'm going to say is continuous. Age, that one's kind of weird. We kind of do round that off. I would say that is discrete. But you could go either way on that. It kind of, you could break it down to the day. I know in my note here it says they are continuous, but age, you could kind of go different ways on that one. We don't usually measure age, we count age. All right, you have to understand the differences between these two guys. It's not terribly difficult to figure this out because we're going to be looking at different statistical models and statistical techniques for dealing with those models. Some will be based on whether or not it's discrete. Some will be based on whether or not it's continuous. I'll be introducing it with discrete and then later on in the next chapter moving over to continuous. So this chapter focuses on discrete probability distributions. So how to construct a probability, as long as it's discrete, probability distribution? It's real similar to just making a frequency histogram. You make a frequency distribution with all possible outcomes, find the sum of the frequencies. You remember this has to equal 1 when you add them up, otherwise you can't make it because it's not then a true probability distribution. Find the probability of each thing. So this is very similar to like what you saw with the dice earlier. The percentage of times you got a 3 on a die, that kind of thing. Again, you just always want to check to make sure it adds up to 1. If it doesn't add up to 1, then you've got to go back. You missed something. You got to fix it. Anyways, you just make a bar chart at that point. Here's a probability distribution of retired persons. Okay, so here, no particular order right here. Here's they're sorted, and I've got them in classes. And of course, one of the differences, this stuff doesn't necessarily have to be a histogram. I can make it a histogram. It doesn't have to be. We can use bar charts for some of this stuff. Bar charts are perfectly appropriate for some of our probability distributions. But if you want to break it down into classes, then technically now we're talking about a histogram. But you've got your frequency, and then 3 out of 24, 3 out of 24, 9 out of 24, so on and so forth. And of course, it all adds up to 24 out of 24, which is 1. So yes, I did this correctly. And then of course you can see right here that this one's way more common. Kind of switching gears here a little bit. Now I've discussed what a probability distribution is. When we're working with probability distributions, a lot of times we kind of want to know, well, what's the average thing that we expect to happen? When I talk about the average, the term mean should pop into your head. And of course, what we expect to happen, the word expected fits right into that, and we refer to this as expected value. You may have heard of this before. Depends on if you're in my class. A couple of years ago, I discussed expected value in my college algebra class. There is a formula that goes with this. This one you probably want to write down, and you're going to see it at the top of the next screen here. So don't freak out as I switch slides because you'll see it again there. But all it is the expected value. You take the value of each thing times the probability of that particular thing happening. And when you do that with all of the variables you've got, you just add them all together. Of course, this is the summation symbol. You're going to add them all together. This is not really a button thing that you necessarily can do on your calculator. You can do some of this with your lists. If you work with lists, you can do some of this. But a lot of times this actually kind of has to get done by hand. You could do it with Excel actually a little bit better as well. Let me kind of give you an example here of finding the mean or the expected value of a probability distribution. To find the mean, again, we're going to take the random variable times its probability, and when we're done, we're going to add them all up. What we're looking at here is college activities. Okay, you can be, in athletics, you can be, acting, some other sort of clubs, and you're looking at the numbers of activities that some college students are involved with. So some kids are in 2 activities, some kids are in 3 activities. My random variable here is how many activities kids are in. And of course, some kids aren't in any activities. What you're seeing here is then their frequencies. That's not the probability of it, it's just the frequency, but we need this to get the probabilities. There's a total of 320 frequencies here if you just add all this up. So then the probability of being in no activity would be, of course, 19 out of the 320. One activity is 39 out of 320, and so on and so forth. You can switch it over to decimals at this point or later, but then what I do is I take this column times this column. This is the x, the random variable, times the probability of the random variable, and I get these values over here. If you're going to try this on your graphing calculator, you can go to Stats, Edit, go to your lists. You can enter data here. You still have to kind of calculate the probability separately, but you can actually program it. You can go to another list, and let's say this is list 1, and this is list 2. You can say, hey, let list 3 be equal to list 1 times list 2. And it'll actually do that multiplication for you so that you don't have to go back and do every single one at a time. But then you still got to add them all together, and that gives us the mean. Now this might be a sample mean, it might be a population mean. In this case, I'm looking at the entire population of a group of students, so that is a population mean. But what this can be interpreted as then would be, hey, if I was to pick a bunch of students at random and average out how many activities that group are in, this is the average number here, the mean, or the expected value. Now this might not be a nice discrete number. Notice this is a decimal, 3.3 activities. Nobody's in a 0.343 of an activity, but the expected value doesn't always turn out to be discrete. In fact, most of the time it doesn't turn out to be discrete. Variance. So if we have our mean, we can also find our variance, and then of course from that we're going to find our standard deviation. You're going to start to see a theme here between variance and standard deviation that'll be similar to what I've already discussed, that there's a relationship between these two. And we've discussed already to a point what variance is. It's how much does the data vary from the population mean. And you see that right here in the formula. This is one particular random variable. There's the population mean. There's the difference between them. How much is it different? But then we square that and we multiply it by the probability of that. So it's kind of like what we just did to get the mean, but we do have to find the difference here and square it before we multiply by the probability of that random variable. When we add all them together, that gives us the variance. Of course, we can go ahead and find the standard deviation then, because standard deviation is always the square root of the variance. And so we can do that here. And here you can see I've actually programmed this into an Excel document to do the same thing. This is still those kids involved with activities graph here. So over here, I set up my computer to do this. I had the mean. I had it go back and I said equals, and then I did this number minus this number. So I clicked this cell, and then I said minus, and I clicked this cell, and then I hit enter. And sorry, this actually the equal sign would have been here. And then I copied. I don't know if you remember doing this, copying formulas. I just had to copy the whole thing down. So you can do them one at a time. You can do these in Excel. Excel works pretty good for doing these things. Actually, I apologize, I'm not quite done yet. So I had it equal that, and then I had it square that. If you just put in SQT into your computer in Excel, it's going to come up to square it. And then I went times, and then I went times our probability, which was this cell. And it doesn't matter that it's a fraction. The computer will switch it to a decimal. And so that was kind of a nice way. Otherwise, you just kind of do it all on your own. And notice that gave me the variance when I had the computer add it all together. and then I just took the square root of it. So you can actually take square roots also in your computer. So what does it tell us? Well, this goes back to the empirical rule. Okay, so it would be that about 68% of the students would have participated between 1.5 activities and 5.1 activities. Where am I getting that? You take the mean, you add one standard deviation, and you subtract one standard deviation. So one standard deviation away in either direction. So 3.343 plus 1.8, 3.343 minus 1.8, that's where I got these two numbers. So most students are participating between 1.5 and just over 5 activities in college. That's how you would then want to interpret that. So we can make some inferences then from our information here. Round off rule, use one more decimal place than the number of decimals used for the random variable. So here the random variable was just one decimal place here. I went to the 10th place here. Okay, so we still have unusual. Remember that unusual is more than 2 standard deviations away. So in your assignment, you'll be asked to decide if something is unusual or usual. So you'll have to, of course, figure out the variance. A lot of number crunching there. Figure out the standard deviation. Figure out what the mean was prior to all that. Then add your 2 standard deviations up and subtract 2 down. I always call this up. I call this down. And figure out what that is, what your range for usual and unusual will be. If I wanted to do that with the college students, so again, the mean was 3.4, standard deviation was 1.8, so I'd go 3.4 plus twice this to get to the high end, 3.4 minus twice this to get to the low end, and that's what I've got here. Oh, sorry, I didn't even read my own question. I was asking if it was unusual for someone to be involved in 5 activities. No, you could go all the way up to 7 activities before it would be considered unusual. Is it unusual to find someone that is not involved with any activities? Well, you take the average minus twice the standard deviation, and that ends up being a negative number, which of course you can't really be part of a negative numbers of activities, but it's less than 0, so that takes us all the way down to 0, which would say, no, it's not unusual for nobody to be involved with an activity in college. And frankly, guys, when you get to college, it's very busy. This is actually kind of made up data. It's probably a little more activities than most people would actually be involved with. I would say that. All right, going along with the mean of a probability distribution is the idea of expected value. And we're going to kind of finish out today talking about expected value. What do you expect it to be? And I'm going to start off with the idea of a raffle. Notice this is the same exact formula that we've already looked at. In a raffle, you know how it works. People buy tickets and they get a chance that possibly their ticket will get drawn to win a prize. And in this scenario here, there's 1,500 tickets. They're going to cost $2 each. The prizes are a $500, a $250, a $150, and a $75 prize. The question, if you buy one ticket, what is your expected value, or this is also sometimes called your expected gain. You'll see that term as well, expected gain. And I like to approach this from the idea of gain. Well, let's see, what if someone gets the 500 prize, what did they gain? They didn't actually gain 500 because they spent $2 buying that ticket. So they gained $498. That's your random variable. What's the probability of gaining 498? Oh, I see I have a typo there. Sorry about that. But the probability would be one of the tickets out of the 1,500. Now I multiply. Remember, you take the random variable times the probability and end up with a number right there. And you're going to continue that on. Notice I keep subtracting $2 from each prize and times the probability of that prize. And then it gets to all the people that didn't win anything. And accounting parentheses means you lose money. So these are the people that lost $2. Well, there's going to be 1,496 of them. 1,500 minus the 4 people that won prizes, 1,496, and I get a negative $1.99. Then I just add all this together. And this is my expected value. What does it mean? Well, it depends upon if you're talking about the people running the raffle or the people that are buying the raffle tickets. If you're the person buying a ticket, this means that on average, over all of the tickets, they're losing $1.35 each. If you're the person running the raffle, which these are typically fundraisers, are trying to raise money, it means on average, they're going to be making $1.35. So it's a little bit from their perspective as far as what does that number actually mean. Let's take a look at another example here. Let's say we got this spinner game, and you spin it, and if you get to either one of these, you're going to win $1. If you hit here, you're going to win 2. If you hit down here, you're going to win 3. Okay, so then the events, what could happen? These are our X right here, our random variables. What could happen? Well, I could win 1, or I could win 2, or I could win 3. What's the probability of each random variable? Well, it's half the circle. It's easy to do. A quarter of the circle and a quarter of the circle. So I multiply across, and I end up with those, or I add them all together. And then we're going to interpret that. What does that mean? It means, well, if you played this lots and lots of times, on average, you would expect to be making $1.75 every time you played. That's an average. That's why it ends up being a number that doesn't even show up here. $1.75 is not on here. But this is the average over a lot of plays is how you would interpret that. But let's say now that it costs you $1 to play this game. Well, you've got to make an adjustment then, because if you land either of these, you actually don't make any money. You would break even. Here you'd win $1, and here you'd win only $2 because you played $1 to play this. And of course, this is what carnival games are all about. Carnival games are all probabilistic models based off of expected values. Yes, some people win big, but there's lots of people that don't. And so on average, it's going to be smaller. Okay, so here what would happen, I adjusted them, still multiply, still add them together. Now I'd only expect to make 75 cents on average if I played it lots of times. In an actual carnival setting, they've got this calculated out so that for you, this would be a negative number. For them, they would look at it as a positive number. That's how they know they can make money out of lots and lots of plays. So let's take a look at another carnival game. Let's say you walk up to a carnival game and they're going to ask you to pay $3 and you get to roll a die. And whatever number it lands on, they pay you that many dollars. So it lands on a 4, you get paid $4 and you just won $1. So this is what could happen. I could roll a 1, 2, 3, 4, 5, or 6. Each of them, of course, have a probability of 1/6. And so that's what I would end up with right there. My expected value prior to taking the fact that I paid $3 to play this into account, my expected value would be $3 and real close to $3.50. But of course, then I would have to go back and go, well, wait a minute, I did pay $3 to play this game. So you're really only looking at, you'd be averaging 50 cents a play. Now, if you were running the carnival, you would quickly go out of business. And so they wouldn't like this expected value. They'd want to tweak that a little bit and make it somehow, they need this to be a negative number for you so that it can be a positive number for them. Let's take a look at the same game, but this time I want to show you instead of, so here at the end here, let me go back to this. We had to kind of make a mental adjustment. Another way to do the same exact problem is to make the adjustment at the beginning. Just realize if I roll a 1, I'll have lost $2. If I roll a 2, I'll have lost $1. So I just do my $3 subtraction right from the start. Then I don't have to make any adjustments. Same exact turnout, you still are averaging over a lot of plays. This is again an expected value over many, many, many trials. You're on average expecting to win 50 cents each trial. I want you to try it, but this time I bumped the price of the game up to $4. I want you to pause it and give it a try. All right, hopefully what you ended up with was, actually, I think I was supposed to have a negative here. Negative 50 cents, I believe, is what it was supposed to end up being. And so that would be that one. Let's take a look at something that's a little bit more, everyday-ish, instead of carnival games or gambling, because that's basically what we were looking at there was gambling situations. Let's take a look at another kind of gambling. And this is really what it is. You are gambling when you buy insurance. You're gambling on the fact that at some point that insurance company is going to pay you for whether it be a car crash or your house gets struck by lightning or you break your arm and have to go to the hospital. Whatever it is, when you buy insurance, you're essentially gambling that at some point you're going to have to cash in on that particular insurance policy. So a few years ago, I looked up some information, and I'm just going to give you a heads up. This was really difficult to find any information. They keep this stuff really secretive and locked down. But I was able to find some information, and that's why it's kind of dated. I had to go back to 2013 to find any information here. In 2013, 7.3% of all vehicle crashes involving 15 to 17-year-olds. Those crashes on average cost $2,587. Okay, so when they had a crash, on average, that's how much they cost. Now you might be looking at this one where the car is like practically totaled. But realize a lot of crashes that teenagers are getting into, they're not like major crashes. A lot of them are just fender benders. $500 here, $600 there. Then there are some big expensive ones that people have to take ambulances rides to the hospital. Unfortunately, things like that, which of course drives the mean way up. But a lot of them are actually fairly cheap. So this might surprise you a little bit that the average cost was actually this low. If during the same period of time, teenagers, again, I'm looking at specifically ages 15 to 17, paid $1,400 a year in their premiums. Of course, this varies a lot between boys and girls and good grades and bad grades, and is it full coverage, is it liability only? There's all kinds of variables here, but I'm averaging them out and just saying, okay, on average, they're paying about $700 every 6 months. I want to find the expected value of gain. Okay, what are we getting from having car insurance? What are we gaining from this? And decide whether or not we're getting a good deal. So it's going to look something like this. Let's say that you don't get in a crash at all, okay? Now notice, the percentage isn't huge. I mean, it's not great, but it's not huge of how many crashes percentage-wise there were. 7.3% got into a crash, but that means 92.7% did not get into a crash. Those people, well, they just lost their money, okay? They paid their premiums, $1,400 for the year, but they didn't really actually gain anything from it. I know you can look at not having a crash as a gain. I would look at it as not have as a gain, but financially, they didn't gain anything. They didn't benefit at all financially from having insurance. Now, some of them did. Some of them, 7.3%, did gain from having insurance. So you take the average cost. Here's the part most people forget. The insurance company didn't actually lose out at $2,587 on average because those people were still paying their premium. So they only lost out on the difference here. So I got to subtract. Lots of people forget that, hey, I paid money to get them to pay me money. And so it's actually, you're only gaining the difference. So I'm going to multiply straight across. And of course, that one's a big negative number. Again, we use parentheses here as negative numbers. That one's a positive number, but you can see it's actually a very small positive number because there weren't that many people that actually got in crashes. Now, again, this isn't a small number, but it's not 50% either. The expected gain then is a negative $1,211.15, which notice isn't a whole lot different than what the premiums were. If you ever wonder why people that work in administration for car insurance companies drive really nice cars themselves, it's because they make a lot of money. There's a lot of money in the insurance sector of our economy. Now, if this type of probability question interests you at all, this is actually a very simple version of a what's called an actuarial science problem. Actuarial science is actually a career field. There's a lot more to it than this, but this would be like baby steps towards this, where actuaries they calculate out probabilities and they help insurance companies decide what they should be charging in premiums in order for them to, of course, make money. So it's a ton of probability stuff, and there's more to it than that. You should do a little research if you're interested. But I will say this is one of the top paying career fields in the U.S. Year after year after year. Actuarial science people come in with some of the best salaries, some of the best working conditions of any job out there. Not necessarily the highest, but they do pretty well. We'll just leave it at that. All right. Page 227, number 1 through 27, take a look at those. And when you do your homework, I talked a little bit about using the lists in your stats program to do some of the calculations for you. The homework's going to help walk you through some of that a little bit. So that may be really helpful to hone those skills and see how that works. Have a good day.